Yes, we are live now.
Okay, perfect. So I guess we can get started. Hello, everyone. Welcome to another Safari Live seminar. Today is my great pleasure to introduce you Professor Amro Awad. Amro is currently an associate professor and leads the Secure and Advanced Computer Architecture Research Group at NC State. Before joining NC State in fall 2020, he was an assistant professor at UCF. Amro received his PhD degrees from NC State University in 2016. During his PhD, he had several collaborations with HP Labs and AMD Research, and he published several interesting works in top-tier conferences. So today we are looking forward to his talk. So Amro, feel free to start whenever you want. Thanks.
Right. Thanks, Mohammed, for the introduction. Hello, everyone. It's my pleasure to present today at Safari Live Seminar. Today, I will be presenting about our efforts on high performance and persistent security support for emerging memory architectures. So a little bit about myself. I joined NC State in fall 2020, where I'm currently an associate professor. Before that, I had several stints at various US government national labs and industrial research labs. At NC State, I currently lead the Secure and Advanced Computer Architecture Research Group, where many of the work I will present today is a result of its excellent students. And the general research area of interest to me is computer architecture, memory architecture, and hardware security. So the rest of this talk will be organized as follows. I will start with a high-level overview of the various research thrusts that we are pursuing at SACA. Following that, I will get to the main topic of this presentation, which is secure persistent memory, where I will discuss the motivation and background to realize persistent security support, what are the challenges to do so, and our contributions to overcome these challenges. Later, I will touch on a recent research thrust that we have been pursuing related to data protection in accelerators and secure integration of accelerators in future computing systems. And finally, I will touch on current research directions and future research directions that we plan to pursue. So at high level, my research team and I have been working on different topics, including the integration of emerging memory technologies in future computing systems, where we looked at technologies such as non-volatile memory and how they could impact performance, lifetime, memory management of the system, and how we could potentially optimize for those. In addition to that, we have been also looking at the security implication of integrating these various types of new memory technologies and how they could potentially impact today's security implementation. We also have worked looking at new system architectures, such as disaggregated memory systems, where we have explored and investigated the performance impact of such architectures, scalability, memory management, and optimizations for these type of architectures. Moreover, we have also explored or have been exploring secure integration of accelerators and data protection in accelerators, how to do this efficiently, and how to adapt today's implementations for future architectures in accelerators. And finally, we have been also exploring performance isolation for safety critical systems, especially when we are running safety critical tasks in computing systems where there could be shared resources such as cache hierarchy or memory controllers. How can we ensure complete performance isolation that would enable certification of these systems for high assurance isolation? All right, so before we get to the main topic, let's think together of if we want to assume the computer I'm using to present now from is secure or trustworthy. What does this mean? As the motherboard I have in my computer, similar to what you have in your computer or laptop, which contains tens, if not hundreds, of components that could potentially come from different vendors, could follow different supply chains, could go through different design stages. All of them are trusted. And it also means that they have been integrated also securely, and the supply chain was not impacted. However, as the number of these components is increasingly large and ever sophisticated supply chain, this is no longer the case. So there has been recent articles or basically findings about potential malicious components injected throughout the supply chain and suspected to potentially enable compromising certain systems. In addition to that, there have been a lot of academic works that demonstrated the ability to fabricate and manufacture chips or components that would look completely benign. However, they are equipped with malicious functionality. For example, what you see to the left is memory modules, similar to what you would buy from your favorite computer store or from Amazon. And in fact, it contains capability to exfiltrate your data using Wi-Fi signals. So this sort of challenges how we define air-gapped systems, because if you think your computer is not connected to the internet, your data is secure, still with malicious components, you could exfiltrate sensitive data. So what we learn from this is that we want to reduce the amount of trusted components in our computing systems. Accordingly, a realistic threat model would usually only trust the system on chip or the processor chip, and anything outside it, including the memory modules or storage, are considered to be potentially malicious, counterfeit, or replaced, or vulnerable to attacks. And in addition to that, external buses on the motherboard are also vulnerable for physical attacks. These attacks include snooping contents, altering or replaying transmitted packets. All of these are realistic assumptions about potential threat models, especially as our computing systems are further and further far away from our physical control, right? You can think of cloud systems or edge computing. Now let's look at how to this.
Sorry. Yeah, I have one question, Amro.
Mm-hmm.
So about the first item that we can trust the SoC and processor chip, don't we have hardware trojans that can be added to these chip? I couldn't understand this. I mean, how can I trust the processor chip?
You can, but you have to have a trusted compute base, right? So eventually you are taking the risk of assuming large number of components is trusted, but to basically enable better security or reduce your attack surface, you would usually trust less component or have a smaller attack surface. So yes.
Yeah, I understand that we want to trust as less as possible. I mean, less number of components, but the fact that we should trust only, I mean, processor chip. So what makes processor trusted? I mean, trustable, because they can also have hardware Trojan, or I don't know. Yeah, I'm not very familiar in this area, but
yeah, that's a good point. So usually it's easy to do attestation for the processor chip or SoC to verify its authenticity, and the firmware and the original software that it's running. That's basically the main reason. The other reason is you could guarantee potentially the supply chain for the processor chip. Now, does this mean that we always trust the processor chip? Not necessarily. What I'm trying to say here is we could potentially focus on ensuring only the processor chip is trusted, instead of having to do the effort for every little component on our system. Let's maybe pay extra for buying the processor chip from a vendor we trust, or a vendor that provides enough security compliance and transparency and can be verified.
I see. Okay, yeah, thanks a lot. I'm sorry for the interrupt, I guess.
No problem.
We're going to interrupt your talk.
No problem. Please feel free. And this is meant to be an interactive talk, so please feel free to ask questions.
Sure, thank you.
Yeah. So this is your typical computing system today. Whenever you are powering on your system, the execution starts from a read-only memory that is usually securely connected to your processor chip, whether on-chip or through secure connection. And this is the first code that will start executing. Now, this has to have its integrity, confidentiality, and freshness guaranteed. And there are many ways to do that. And this starts executing in your root of trust within the processor chip. Your root of trust will be responsible of initializing various interfaces. Then you will start loading larger piece of code, which is, let's say, the platform firmware, and that will also execute in the root of trust. However, since these codes are small enough, they can be loaded, verified, and then start executing from within the chip. However, later on, as we start moving to larger code bases, such as bootloader or the operating system, all of those become large enough that you cannot load them all at once or load them at once and verify them. You have actually to load them in memory and execute them from external resources or by accessing external resources actively. So what does this mean is that at the steady state, you will be mostly accessing your data and executables in the external memory modules, which means that your memory has to be protected, your external memory bus has to be protected as well. Otherwise, all of the potential attacks we discussed earlier are feasible. So if we want to classify security levels based on the stages we have seen, the highest level of security would ensure confidentiality, integrity, and rollback protection, whereas the lowest level has no security or guarantees at all. So what we have seen is usually the boot ROM, if it's on chip or securely connected to the chip at manufacturing time, you will have confidentiality, integrity, and rollback protection guarantees. Same goes for the platform firmware. If you are able to load it, decrypt it from within the chip and execute it from within there or from within a secure storage, you will have all of those guarantees available. However, as we start using the external main memory, we will end up actually risking the fact that if our memory is not protected, we go with no security, which means that your codes, your data, and the memory could be tampered with, replayed, and compromised in terms of confidentiality as well. So this motivates the concept of secure memory. So what secure memory is, it assumes that only your processor chip is the trusted compute base, whereas whenever your data is sent out off chip, it has to be encrypted. It has to have its integrity verifiable and replay protected. So every time your processor chip is writing to the memory, it needs to encrypt the data. It needs to calculate authentication tags. Also, when it reads it back, it needs to be able to decrypt it only within the processor chip boundary, authenticate the data, and be able to verify its freshness. There exists a lot of commercial support for that implement either all of these protection guarantees or any combination of them. So for example, we have Intel's SGX, we have Intel's TME, AMD's secure memory encryption, SEV, etc., and many other supports. Usually these supports for secure memory are enabled in confidential computing in cloud systems, whereas the threat model even assumes the operating system could be untrusted, but that's besides the main concept of secure memory. So let's look at how all of these protections are implemented in general. So for confidentiality protection, usually counter mode encryption is used. And in counter mode encryption, as you can see on the right side, the memory is divided into blocks as usual memory, 64-byte block, and each 64-byte block is encrypted using a specific metadata that corresponds to it. For example, encrypted block 0 will be encrypted and encrypted with aid of a particular metadata that is associated with it. And what this means is every time you are trying to write a block to the memory, for example, block 0 to be written to this location and stored as encrypted block 0, you need to encrypt it by first reading the counter or nonce and use it along with the address as initialization vector to generate a one-time pad that will be bitwise XORed with the block to generate the encrypted block. Now, why we need these two to be the initialization vector? Usually the reason is to provide temporal uniqueness and spatial uniqueness. By temporal uniqueness, I mean, if the same plain text value is written again and again to the same location, it should appear as a different ciphertext value. For example, here, when you are writing zeros to the first encrypted block, you will update the counter that is associated with that block. Accordingly, next time you do encryption for the same value, it will appear as completely different ciphertext. Accordingly, attackers cannot observe the temporal similarity of data being written to the same location. Perhaps you have guessed this by now already, the address provides spatial uniqueness. So even if we are writing the same value to different addresses in memory, they should not look as similar values in terms of ciphertext. And the address here gives us this spatial uniqueness. And by doing that, we prevent dictionary-based attacks and attacks that rely on analyzing the frequency of similarity in natural text or data. To reduce the overhead of round trips to memory every time you are reading a counter and updating it to enable encryption, decryption, and encryption respectively, a counter cache is used where it caches the most recently used counters. And counters usually are grouped into counter blocks to match the memory access granularity. So you can think of a 64-byte containing 8 or 64 counters that could be cached in the counter cache and hence exploiting the temporal and spatial locality of access to the memory. All right, so as we now understand how counter mode encryption work at high level, let's look at how integrity and freshness is guaranteed. Usually the way to verify integrity or authenticity of data is to apply message authentication codes. For example, a message authentication code could be calculated for each encrypted block and written along with it. And by having the authentication key only known for the secure memory controller, similar to the encryption key we saw earlier, then whenever we are reading data and read its message authentication code and its message authentication code matches what we expect based on our authentication code or key, we would verify the authenticity that this data has been written by the processor chip. However, this is vulnerable to replay attacks because an attacker could potentially replay a pair of encrypted block along with its MAC, but from a previous write to the memory. To eliminate that, freshness has to be guaranteed, which means we need to guarantee blocks are not replayed. To do that, usually integrity tree is used. However, prior work realized that it's sufficient to ensure the freshness of encryption counters to guarantee the freshness also of the encrypted block. That work is called Bonsai-Merkle tree. I will not go through the details of it, but we will take that and use the integrity tree just built on top of the encryption counters. By doing that, you can build an integrity tree where integrity tree essentially is levels of hashes or tree of hashes where the leaves are the counters, the next level will be the hashes of its immediate children, then these hashes will have actually parent hashes, etc. Eventually, the root of the tree, you can think of it as a single hash value that represents the whole content of the leaves. Every time you are trying to verify a counter, you need to verify it through its path all the way to the root. Same as when you are updating a counter, you need to update its path all the way down to the root. However, the tree nodes are usually stored in memory because the tree nodes are large enough. Usually you would have 10 or 9 levels of integrity tree, if not larger. And the arity is high as well. Usually you would have 8 children for each node. And accordingly, these cannot fit on chip. And accordingly, to improve the efficiency, you would cache these nodes. This would work well in the sense that first, it will allow us to reduce the memory access to bring these nodes. And the second thing is that you will potentially avoid to go all the way to the root. For example, if I cached this yellow node already verified, when I'm Xing this particular counter, I only need to see if its hash value matches the hash value stored in this node. I don't need to go all the way down to the root. However, if this one is a miss from the cache, I need to verify it through its parent. If it's a miss, etc., I will go all the way down to the root. All right, so now we understand the integrity protection and authentication and how confidentiality is protected. So all of those apply for typical memory, whether it's DRAM or persistent memory. So the question is, what does change when this implementation is to be adapted to persistent memory? What are the challenges that we will see there? Before that, let's discuss what persistent memory is. In simple terms, persistent memory could be defined as a memory that is capable of retaining its data even after power outage events. A way to realize persistent memory is to use emerging non-volatile memories. Examples such as 3D crosspoint and many other promising technologies showed potential for performance comparable to DRAM, huge densities and hence capacities. For example, the memory module you see on the right side could potentially be a half terabyte memory module. In addition to that, it enables crash consistency, which means that applications that could take advantage of the persistence capability of memory could potentially enable recovery after power outage or crash events because it routinely saves the data in the persistent medium. In addition to that, emerging NVMs promise ultra-low idle power because unlike DRAM, it does not need to be refreshed very frequently. There are a lot of different memory technologies, emerging non-volatile memory technologies that have different use cases and potential. However, in terms of challenges, the main challenge is security because as you have heard by now, it retains data for a long time, which means the attack window is large enough. If an attacker is able to physically obtain my memory module, it can, with minimal efforts, scan it and reveal any sensitive data. Accordingly, protecting data in non-volatile memory is quite important. In addition to that, due to the physical characteristics of these technologies, it usually has limited write endurance, which means it can be written, for example, a few million times before a cell wears out. Also, due to the nature of how we program the cells of these technologies, usually slow and power-consuming write operations are needed for these type of technologies. Well, the main takeaway from the last 2 points is that we would like to reduce the number of writes as much as possible for these memory technologies. Now let's look at how persistent applications usually take advantage of these persistent memories and why would that be challenging with today's secure memory implementation as we have seen it earlier. So this is a persistent application that would usually access persistent data in the memory and update it, then explicitly persist it. For example, it would update it usually using your typical store operations. However, it explicitly flushes it to the persistent domain using a write back or a flush instruction to ensure that it's persisted or saved in the persistent medium. However, since we have secure memory, we need to protect that data, which means that we need to encrypt it, update its encryption counter, update the integrity tree, etc., and then calculate the message authentication code, and then do the write to the persistent memory. However, one issue here you probably have seen is that upon a crash, we will have an inconsistency between the security metadata we have in the memory and the persistent data, because the security metadata were updated in the volatile metadata cache in the non-persistent domain, whereas the data was persisted in the persistent memory. So we have a stale encryption counter used than the one used for encrypting the data. Same as for integrity tree nodes, they could be basically out of date. So when we have the power back, we will fail to recover these nodes. We will fail to recover or verify the integrity of data, and hence the recovery will fail. So the first challenge is how to enable recovery of security metadata to their most recent value before a crash. Well, the naive way would be that for every data persistence operation, we have actually to update all the security metadata in the memory. However, this will incur high performance overhead and will make our memory wears out pretty quick. In other words, using a write-through mechanism for the metadata cache would be very ineffective, especially for the non-volatile memory. Now, our contributions include Osiris, and later works looked at how we can potentially enable recovery of security metadata to their before crash status with minimal write operations. So if we want to divide this into two steps, the first step would be to enable recovery of encryption counters. And the second thing would be to rebuild the integrity tree based on the encryption counters. However, we know for certain, or the most common type of integrity trees, just be able to recover the leaves, which are the encryption counters, and having the root of the integrity tree always up to date would allow us to recover or reconstruct the integrity tree. This assumption holds for the typical Merkle tree, for now, dismissing the fact that it might take a long time to recover or rebuild the integrity tree. So let's see how we enabled recovery of encryption counters in our prior work. So if we want to enable recovery of encryption counters, this could be systematically divided into two steps. The first step would be to identify if a counter is stale or not. For example, this is your memory status after a crash. You want to be able to identify which of these encryption counters are older than the value used to encrypt its corresponding block in memory. Now, after we know this, we need to be able to know actually what was the most recent value that was used to encrypt these blocks where their counters are stale in memory. The challenge here is that counters could have been incremented many times. In other words, it's not a simple relationship between knowing that it's stale and identifying what would be the value was used for encryption. For example, a counter could have been updated hundreds or thousands of times before it was lost from the metadata cache, which means we would need to have actually a lot of trials here. The second thing is that the only way to know if a counter was recovered correctly is through the Merkle tree root. However, with having the counter could have been potentially incremented many times, and most importantly, multiple counters are lost. This would make it computationally infeasible to try all potential combinations to find out if we could get the root of the integrity tree we expect or not. So what we did in Osiris at Micro 2018 is that we realized that the error correction codes, which are usually used to detect errors in memory, can be used also as a sanity check to indicate if the decryption operation happened correctly. And by happened correctly here, I mean it happened with the correct encryption key and correct metadata, in other words, counter. So currently, the error correction code algorithm would calculate a tag on the plain text, which is the ECC, and this can be encrypted along with the plain text to generate the whole encrypted block that can be written to the memory. However, upon decryption, we check out the counter we have in the memory, and if the counter is stale, essentially it means that you are generating completely different path than the one was used to encrypt this block. Now you are trying to decrypt. In other words, this is similar to trying to decrypt a file with a different key than the one you used to encrypt it. The result will be completely random or unrelated values. With that, very likely your error correction codes will indicate errors. With large number of code words within your cache line indicating errors, we will know that something went wrong. Obviously, we can try the next counter value by incrementing it. And if natural number of errors or no errors at all are seen, we know that this is likely the counter that was used to encrypt the block. One thing that you probably already observed is, what if there are actually natural errors? How can I distinguish between those and using a stale counter? To do that, we had actually thorough analysis that indicates how many code words could be flagging an error within a cache line. Could be enough indication for us of whether it's a natural error or if it is using or the decryption went wrong. Without going through the details of that, I refer you to read the paper if that's of interest to you, but it was easily distinguishable if the error was due to natural error or because of wrong decryption, because in wrong decryption, the number of code words that are faulty within a cache line is very large, and you can easily detect that. All right, so in terms of design changes, the read operation sequence would just change briefly, such that you will first do the decryption, then verify the ECC, because the ECC was encrypted along with the data rather than calculated over the ciphertext. Whereas also in the write operation, similar sequence will have to happen. For example, we will have to first calculate the ECC, then apply encryption to the data before writing it to the memory. However, one extra thing we have is we limit the divergence between the value used for encryption and the value currently in the NVM memory. Because without that, we might need to do lots of trial and error, as you have seen in the previous slide, to find out if this is the correct counter or not upon recovery. So to limit that number of trials and bound it, we limit the number of updates to a counter to n before it has to be persisted. So every nth update to a counter, its value has to be persisted in the NVM memory. So with that, we were able to reduce the number of writes significantly, because now we do not need to update metadata in memory with every write. Instead, we are able to recover it using error correction codes. So what you are seeing to the left side is the number of writes reduction, and in the right side, you are seeing the execution time. And in summary, we were able to reduce the number of writes by 48.7% and reduce the performance overhead from 51.5% to 5.8%. All right, so we thought we are done at that time, but we realized that, well, yes, we are able to recover the system, but that's not sufficient, because recovering the encryption counters, as we have seen there, would have to go through every block in memory and use its ECC to recover the counter, and then rebuild the whole integrity tree. And what we realized is that with the sizes of memory NVMs promise, which could be in terabytes, this iteration over all the blocks and rebuilding the integrity tree can take significant time. And what we have seen is that the recovery time could take hours. And we demonstrated this challenge and problem in Anubis in SK 2019, and we solved it also for different types of trees in Phoenix in TDSC 20. So what we have done in Anubis, we realized that you could potentially track the lost security metadata and potentially lost counters securely without the need actually to just obliviously rebuild your whole integrity tree or recover or check every counter in your system. By doing that, we were only bound to the number of counters could have been potentially lost and integrity tree nodes impacted. With that, we were able to reduce the recovery time from hours to less than 0.5 seconds with only 3.5% performance overhead. So the third challenge was errors in large and long-living integrity trees. So integrity trees has a problem is that as you go higher, closer to the root, errors would be more impactful in terms of system availability. For example, errors closer to the root would render a large percentage of your memory unverifiable. I'm talking about uncorrectable errors. Accordingly, what we have done in Micro 2021 is we hardened the integrity tree such that even errors or basically a harsh environment would not lead to degraded robustness of the system when large integrity trees are involved. With that, we were able to achieve the same reliability level of no security at the same time with only 1% performance overhead. The fourth challenge is high performance overheads for persistent applications. The common wisdom is that write operations are not in the critical path, which means that we do not care about doing them fast, but perhaps you already got that from what we have seen in the persistent application example. Persistent applications would wait until a write operation is persisted in the non-volatile memory medium. So it directly impacts its performance. So in the fourth challenge, what we observed is optimizations that vendors add to processor chips to speed up the persistence operations by including persistent buffers on chip can be rendered ineffective if the security operations are implemented before insertion in the persistent domain. So to improve the performance of secure persistent applications, we had work in Micro 21 called DOLOS, which looked at decoupling the security implementation and allow lightweight protection when inserted on the on-chip persistent buffers of modern processor chips. And we have other related challenges we have addressed. For example, in HPCA last year, we have looked at the challenges for realizing file system encryption when NVMs, when file systems are accessed directly through load and store operations. Typically, your file system encryption will be implemented in software, in the software path. However, if we want to untap the potential of NVMs, we would like to be able to access the files using DAC support, where you could potentially memory map a file and load and store directly to the file content. However, that's not feasible without hardware-software co-design, which we demonstrated in HPCA 2022. In addition to that, we have observed that low latency flash or storage drives could potentially be burdened by software security implementation for decryption and integrity verification of storage content. And accordingly, in HPCA 23, we and our collaborators, we devised a design that looked at processor side support, hardware support that would enable efficient hardware-based decryption and integrity verification of data in NVMe drives. And finally, we have observed that in extended persistent domain systems where your whole cache hierarchy can be flushed upon power outage event by relying on backup battery or large capacitors, the security support would significantly enlarge the amount of energy we need to drain the full cache hierarchy. Because when we have security support, the number of memory access we need upon draining the cache hierarchy could be very large, especially if we have sparse content inside the cache hierarchy. This will mean poor metadata locality, and you would end up for almost every write operation or draining operation, you would end up having to do many memory access in memory. So we demonstrated a solution called Horus and Micro last year, which described a design that can reduce the draining energy significantly while enable secure memory. All right, so in conclusion, integrating NVM while supporting secure memory introduces new challenges. System recoverability requires careful handling of security metadata, and time for security metadata reconstruction can impact system availability. Now let's move to the second part, which I will briefly touch on our recent efforts on. So many of you already know about various types of accelerators, including neural processing units, deep learning accelerators, GPUs, etc., that promises high energy efficiency and performance advantages over conventional CPUs. However, there are two main security challenges and hence objectives, which is first, secure integration of these accelerators. If this accelerator is potentially malicious or buggy, you want to be able to sandbox it such that it only accesses its corresponding data rather than other applications' data. In addition to that, we need to have efficient mechanisms for protecting the data processed by accelerators. This data could be confidential or proprietary deep learning models or personal data, etc. So what we have observed is that the conventional way of implementing secure memory, as we have seen it in the previous part of this talk, it can incur significant performance overheads. And the reason for that is big part of your memory bandwidth will be consumed by access to security metadata. As we can see in the right figure here, more than 50% of your memory bandwidth will be consumed by access to Merkle tree, to message authentication codes, and encryption counters. And accordingly, we looked at a novel design that leveraged three main insights that could potentially reduce the memory bandwidth consumed by security metadata. In particular, our first observation was for GPU workloads have a lot of similarities between data that is being accessed in the memory. And what we have found is that you could potentially get away with verifying the data content and its authenticity without bringing message authentication codes. Later, I will show you how this magic can happen, but we realize that it can be securely and statistically proven to be as secure as MAC functions. In addition to that, we have observed that data in GPUs or large percentage of data could be infrequently updated, which motivated a layer of compact counters where you could start with small counters and hence good locality and cacheability. And if you exceed that number of writes, you could potentially start using a larger counters. In addition to that, we have observed that there is a mismatch between the memory access granularity and GPUs. For example, usually GPU memory is accessed by sector granularity, whereas the typical designs for security metadata is using 64-byte blocks or larger. And hence, we redesigned our security metadata and architecture to fit the access granularity of memory to avoid overfetching. So to better understand the first insight, let's think of this block being written to memory, and we are assuming an encryption scheme where it has good avalanche effect, such as AES-XTS, where any bit change in the ciphertext will lead to so many changes upon decryption, in simple terms. So this is a 16-byte sector being written. Assume that we are tampering or changing these parts of the ciphertext after it's encrypted. Now, upon decryption, it will lead to completely unrelated data. It's sort of random data because any bit flip will be kind of diffused on the ciphertext, which will lead to completely, well, not completely random, but nearly random data. So with that, if we have the ability to remember what a normal value or predicted value would look like, based on what we have verified recently, we could quickly realize if these values look normal or something that similar to what we have seen recently. And by doing that, we could potentially avoid bringing the message authentication code because we know if any tampering occurred, then most likely we get random values that is very improbable to get you data similar to what you expect to be normal or similar to what you have recently verified. So by exploiting these observations and designing Plutus, we were able to improve the throughput of GPU by 11.65% and save around 48.14% of the needed security metadata bandwidth compared to state-of-the-art approach. The second challenge is high performance sandboxing of accelerators. And the typical way to do that is that you add an access control unit similar to your memory management unit, and every access to your system memory has to be translated and verified. However, that would become a scalability bottleneck and would introduce a lot of performance overheads. So today's approaches or optimized approaches rely on either allowing accelerators to do the translation themselves and do the access control and then access the system physical memory directly with physical address. In other words, bypass any access control. This will give you the highest performance because you can rely on the internal caching structures of accelerators. But obviously, that's a high security risk because we are obviously assuming the accelerator is trusted, the accelerator is not buggy, the accelerator will only access the system physical memory addresses that belong to it, which is, again, an ambitious assumption. Approach 2 is to maintain additional layer of access control decoupled from translation. For example, allowing the accelerator to do the translation. However, the access control unit will verify if the physical address to be accessed by the accelerator is designated as accelerator page or can be accessed by the accelerator based on the permissions the OS or hypervisor has set to the accelerator. Now, with that in mind, there is recent work such as border control, similar as DAC, that leverage this insight. However, this comes at the cost of metadata being very access pattern dependent. For example, even the metadata that is decoupled from translation, which is used to verify the page belong to the accelerator, is still access pattern dependent, and its locality heavily depends on the access pattern of the accelerator. In addition to that, it requires software changes to allocate permission tables that are used alongside the page tables. So page tables are used for translation, permission tables are used for the decoupled access control. It also complicates memory management because now you have two types of tables that you need to handle for each accelerator and potentially for each context. So CryptoMMU, which was published, which was accepted in Micro 23 and will be presented later in October, leveraged cryptographic authentication to validate accelerator translated requests. So what we have observed is that by allowing accelerators to cache translations, but also cache a cryptographic evidence, something like message authentication code that could be supplied with each request, is sufficient for us to allow the access control to authenticate or verify the access. By doing that, it's better in terms of scalability because each accelerator will only need only one authentication key is needed per accelerator, and that can be kept at a CryptoMMU, where it will be calculating the evidence and provide it with the translation to the internal TLBs of accelerators. And at the access time, it verifies the evidence is correct and still valid to allow the access or not. Without going through the details, please attend the presentation in Micro 23. And if you would like more details, I'm happy to share the community version with you. Now, in terms of current research, yeah, please.
Sorry to interrupt. So I have a question here. You just need to one CryptoMMU for all of the accelerators, or you need to specific different CryptoMMU for different accelerators. So I just want to know the overhead of these CryptoMMU here and the scalability.
That's a very good point. So the idea here is that the only thing you need to do is to authenticate the translation request or the request itself, which means the only parallel resources you need within a CryptoMMU is message authentication code engine or hash engines or secure hash engines, which you can have many of them. In addition to that, it doesn't have any other internal structures that could be bottlenecks. For example, you don't need to have internal TLBs or caches to do that. The only thing you need is one key per accelerator or per context, and parallel MAC engines to allow parallel accelerators to access that. So you could get away with one. It depends on how many accelerators, but eventually you will be bottlenecked by how many, similar to anything, right? If you have TLB or MMU, it will be bottlenecked by the number of ports. It will be limited by the number of queues inside it, right? Here, the bottleneck will become basically the hash engines, right?
I see. Yep. Thanks.
Yeah. And by the way, those could be heavily pipelined or deeply pipelined and could be optimized or can be actually parallel of them to allow multiple accelerators and hence scalability.
Yeah. Mm-hmm. Thank you for the explanation.
Yeah. Right, so let's touch on current research directions that we have been exploring. Currently, we are looking at enabling integration of untrusted IPs and high assurance systems. For example, we are looking at systems designs where you could potentially have the interconnect untrusted IP. You are licensing from company X or Y, but you still want more guarantees that it's doing its job correctly and securely. Same could be for the memory controller. Same could be for the cache controller. Same could be for even more aggressively the processor chip. So one part we have been exploring is it possible to add extra logic or wrappers around IPs that we consider untrusted to verify that they are doing their job correctly in high assurance systems. You can think of the memory controller we have seen before. If we add our secure memory controller logic just before the DDR controller IP here, then we don't care whether everything here is not trusted, right? Including the controller IP itself. Now, in addition to that, we have been looking at ways to simulate mixed fidelity models. For example, if we have a RISC-V design, chisel code for a RISC-V processor, your favorite RISC-V processor, and you want to understand how it will perform in a certain architectural model, like what you can have in SST or Gem5, how can we integrate these low-level models with high-level event-based architectural models? So a big part of our effort was looking at how you convert architectural events into actual stimulus or signals that could keep the IPs that you are integrating active and how to translate their signals into architectural events. We have work and tutorials that are upcoming, which we'll announce soon about. In addition to that, we are currently exploring efficient security support for hardware accelerators within the new architecture, such as if we have hybrid memory architecture, or we have memory that is connected through CXL or multi-GPU memory, etc. How can we implement, or how could that impact security support and what we have seen as secure memory in the previous part of this talk? In terms of future directions, we will be exploring chiplet root of trust. How does the survivability of the system and system attestation can be implemented when you can no longer live with a single chip that you trust? Now you could have multiple chiplets. Which one is considered your root of trust? How do you do attestation? Also, how can you minimize or improve the system robustness by the fact that if a chiplet fails, your whole system doesn't fail, because these chiplets could potentially be manufactured differently. They could potentially have different robustness level, and you don't want your system to fail as early as the first chiplet fails. In addition to that, we will be exploring confidential computing for disaggregated memory architectures. Things we'll be exploring, including scalability and efficient integrity verification support, scalable and secure attestation of the system, and confidential computing in these type of disaggregated memory systems or fabric attached memory. The main challenge here is your compute nodes, which could potentially run different software stacks, accessing shared pools of memory, which means that your attack surface is very wide. This complicates access control. It also requires high level or high assurance for security and data protection when it's stored in this shared memory resource. How can we cryptographically guarantee that is challenging because your integrity trees could become very large. They could potentially be accessed and processed by different compute nodes that share data. How can we realize this efficiently is something we will be exploring. And finally, we are looking at the problem where the different IPs that you could potentially license from different companies could be proprietary, and certain startups might be not willing to share with you the detailed simulation model or give you the actual IP to test it for potential system integrators. You could potentially have hundreds of companies that offer different options for certain IP or certain subsystem, which means system integrators will first need to sign maybe hundreds of NDAs to be able to get access to the simulation models and try it out. In addition to that, also startup companies would potentially risk proprietary information to be leaked if they are sharing their IP simulation model, detailed simulation model, or potentially the IP itself to many different potential customers. So what we are looking at here, or we'll be looking at here, is generating a proxy IP that statistically capture the performance model for IPs and can be used for design space exploration by potential customers. It's in very early stage. We have early results that make us think it's possible, but this can apply to many different IPs of which we can do black box cloning or black box capturing of its performance model. All right, with that, thanks for your attention, and I will stop here.
Thanks for the talk. Could you go back to the future direction, the second one? Mm-hmm. Yeah, so here you mentioned there's the third one. I'm very interested in the confidential computing in the heterogeneous compute node. If we let's assume that we have a persistent memory, non-volatile memory-based processing using memory or processing in memory. So do you have something in mind? What could be the, let's say, the threat model for this kind of emerging computing system, computing using memory system?
Yeah, that's an excellent question. Yeah, that's an excellent question. So if I read your question correctly, what you are asking is, for systems such as in-memory computing, yeah, what would define our trusted logic, right?
Yeah.
Yeah. So for in-memory computing, it really depends, right? You usually use it for a higher performance. So if you want to really leverage that, you will likely want to be able to process data directly as plain text, which means you are extending your trusted compute base to include the logic within the processing in memory capability. However, there could potentially be more ambitious approaches that look at differential or privacy preserving approaches, or even things such as homomorphic encryption. Its potential and feasibility for a system that you mainly use for acceleration is still questionable, but it really depends. If you want to trust or extend your trusted compute base to include the logic and the processing in memory, then most likely you would at least need to do attestation. You need to verify that the logic you are offloading data to or will be processing your data is trusted. Is it from a vendor I know has abided by certain security compliance requirements or known for good security practices, etc. Otherwise, you might want to assume it's not trusted and rely on things such as homomorphic encryption or privacy preserving techniques to operate on the data by the accelerator, but without having to decrypt it before it's sent out to the in-memory compute logic.
I see. Do you think there will be more like threatening model compared to the traditional memory, because you kind of like involve the computation in the memory? And for example, let's say that let's assume that we have a side channel attack to the non-volatile memory that we want to maliciously like write a certain place of the non-volatile memory to make it one out in a very short time. This is kind of like a kind of attack to the traditional non-volatile memory. But consider about the processing in memory or processing using memory. We just send the instruction to high-level instruction to the processing using memory unit and let it to do the computation inside the memory. So do you think that is still some opportunities like or there's some like very different ways to do the attack to the processing using memory unit? Something. Yeah.
Yep, this is an excellent point. So what you are raising is quite interesting. You are raising the fact that we are offloading a high-level instruction to the processing and memory logic, but if it's malicious or buggy, it could potentially wear out your memory by writing a lot to certain cells, etc. Right?
Yeah, exactly.
So denial of service attack become harder to detect. For example, if you have certain detection mechanism in your processor side, whether you use performance counters or your memory controller is aware of such potential attacks and is able to detect such malicious pattern, that's easy to realize. Now, this protection mechanism has to be also implemented in the memory resource as well. However, with relation to the secure memory, in secure memory, you are not really trying to stop denial of service attacks. What you are really trying to do is to avoid authenticating and assuming a corrupted data is valid. For example, no one can stop you from damaging your memory module, right? But what secure memory guarantees is that you will not be able to read a data that was tampered with because of the damage you did or because someone tampered with the data, will not be read and assumed benign because our authentication mechanism will detect that. So yes, the threat model here is different than the conventional definition of secure memory, but yeah, it will complicate that because as you rightfully mentioned, it also involves even other layers such as the runtime framework that manages the processing in memory, maybe device drivers, maybe involves compiler, involves lots of layers in the stack that we would need to verify to ensure at least isolation within data that exists in the processing in memory. So yeah, I totally think it would expand the threat model generally assumed for secure memory.
Yeah, it's very interesting to me. Thanks for the explanation. Yeah.
No problem.
Thanks a lot, Amro, for your talk.
Mohammed, sorry, go ahead.
Yeah, I have also two questions. Maybe Rakesh, you can also go after me. So basically, you have only one root of trust, and so when I'm checking in other field like dependable system reliability. So we always try to increase the number of points that they are reliably work in order to reduce mitigate this problem, single point of failure. So are you guys also considering increasing the number of root of trust, or I don't know, is there some redundancy that can provide better security?
That's an excellent point. So what you are referring to as fault containment regions, that even if the root of trust fails, or we still could operate the system correctly. And actually, this problem would arise here a lot in chiplet-based architecture, because naturally each chiplet is a fault containment region. Well, assume it can operate independently or could potentially be reconfigured if other chiplets fail. Yes, the assumption is because of the nature that those could be manufactured independently, you would end up having different root of trust. Now, within each, let's say, chiplet or within each processor chip, does it make sense to have different root of trusts? It really depends on what is considered a fault containment region inside the system, inside the chip. If your chip is designed maybe such as redundancy or dual core lock step, does it make sense to apply the same for root of trust? these are all open questions. I don't think that this is the current practice. Usually what is redundant is the computational cores, the main cores, but yeah, it's feasible. It's just it comes at obviously area overhead. I can't think of a fundamental challenge that stops having multiple distributed root of trust that could potentially operate on lockstep, similar to dual core lockstep.
Yeah, thanks a lot. So yeah, Rakesh, please.
Yeah, thanks for a nice talk. I just had a question on Osiris here, the first work that you presented. So I was just curious, what kind of ECC implementations you tried for this work, and I from what I gather, it's just for error detection. So did you also try more simpler approaches to detect errors, possibly like secure hash functions or something like that?
Yeah, that's a very good point. So the option for having message authentication code is there. Instead of using ECC, we could potentially have message authentication code that could detect if there is a failure, or if there is an error because of basically a wrong encryption counter. However, the main problem here is that if you just persist the message authentication code along with the data and you use MAC instead of ECC, then likely you will not be able to correct errors, because message authentication code, as you mentioned, it will allow us to detect if there is an error, right? Now, you would, by having ECC encoding this capability and just persisting ECC along with the data, it's sufficient for us even to correct errors in the data itself, in the ciphertext. By enabling that, we are providing more guarantees than if the message authentication code was collocated. So usually your message authentication codes are grouped separately where ECC is collocated. There are excellent works that looked at collocating message authentication code with data instead of ECC. But if you have to choose between both, you really want to have the ability to correct the data exist there, if that's the only thing you are persisting or you are relying on. And your MAC could also be persisted, but that's not the part we looked at in Osiris.
Okay, thank you.
Are there any more questions?
Yes, I have a question. Thanks for your great talk. I have questions. I'm working on mobile devices. In my opinion, there's a trade-off between high security and high performance. But I'm mainly working on the high performance and the long lifetime for mobile devices. But I found that the data security takes more important than ever before on mobile devices. For example, several years ago, we can read all the data on mobile devices, but now we hard to do that without root permission. And we also found the data in the mobile devices are encrypted. So here's I want to ask that do you think there's any challenges, specific challenges to do high performance security support for mobile devices? I mean, since the mobile devices have limited power and computation resources and power down anytime.
Yes, I mean, definitely there are parts that you cannot abstract away. For example, if you want to have parallel encryption engines or authentication codes or authentication or hash engines, counter caches or metadata caches, all of those would consume area. And it really depends on the trade-off if you are willing to basically are willing to take extra area to provide security guarantees. Now, in terms of performance, much of these overheads could potentially be overlapped with the memory access latency. So, for example, generation of one-time pad could potentially be overlapped with the actual fetch latency from the memory. So the only thing you would need after the data arrives is a bitwise operation, XOR operation, which is usually a one cycle thing, right? So I would think most of those could be highly optimized for performance to a point that you could hide good percentage of these overheads. However, anything would usually you want to improve performance, it will come at the cost of extra logic or extra caches, etc. That would mean area and potentially power. So yes, the challenge of sitting where in that trade-off we want to be. We want to optimize for area, we want to optimize for performance, we want to optimize for security, we want to optimize for power. I think it really depends again on the regulations, on the vendor, the type of mobile you are producing, right? So I wouldn't think it's impossible, but I don't think there is a free lunch here.
Okay, thanks.
Are there any other questions? Okay, I guess we can wrap up today's seminar. Thanks a lot, Amro. That was actually excellent talk. We enjoyed a lot. And wish you all the best. Thanks everyone for attending and asking questions.
Well, thanks, Mohammed. Thanks, everyone.
Thank you.
Thank you.